A fiery medieval workshop held secrets about light that would not be named for centuries. We celebrate Isaac Newton for unlocking the mysteries of optics, but the true pioneers were anonymous artisans. Their discoveries are still on display today, hidden in the radiant colors of cathedral windows. This is the story of how medieval glassmakers, through sheer craftsmanship, uncovered fundamental principles of light behavior long before Newton was born. By the end, you will see a stained glass window not as a simple religious image, but as a sophisticated scientific experiment. How did these craftsmen achieve such precise colors without any formal theory? And why did their revolutionary knowledge remain a secret for so long? What does it mean to find science in the unlikeliest of places? Inside the workshop, the roaring furnace was the heart of everything. It was not just a source of heat, but a living entity, demanding constant attention. The master glassmaker knew its moods, feeding it with specific woods to reach the exact temperatures needed to transform common earth into something luminous. Their raw materials seemed almost mundane. They started with simple sand, the same substance found on a riverbank. To this, they added potash, derived from burned wood ashes, which acted as a flux to lower the melting point. But the true magic, the source of color, came from metallic oxides. A handful of cobalt would yield a deep, majestic blue. Copper compounds could create either a vibrant red or a brilliant green. Gold, used sparingly, produced a stunning ruby glass, a color so rich it seemed to hold its own inner light. These were not understood as elements in a scientific sense. To the medieval mind, these minerals were imbued with spiritual properties, their colors a manifestation of their essence. The process was one of transmutation, turning base materials into a substance that could dance with light itself. The goal was never to understand physics. It was a sacred mission to build windows that would tell biblical stories to an illiterate populace, using color and light as a universal language. Yet, in their relentless pursuit of perfect hues, these artisans were about to stumble upon one of light's most fundamental behaviors, a principle that would later be called wavelength filtering. They were about to discover that color is not something a glass possesses, but something it does. But the true artistry was not just in knowing which mineral to add. It was in understanding the furnace itself. Each color demanded a specific atmosphere, a precise chemical environment inside the fiery chamber. For a rich ruby red from copper or gold, the glass needed to be melted in what we would now call a reducing atmosphere. This meant carefully controlling the fire to limit the amount of oxygen available. In this oxygen-starved environment, the metal particles would form into tiny, distinct nanoparticles suspended within the molten glass. These minuscule specks, far too small for the medieval eye to see, were the true architects of the color. They did not simply tint the glass like paint. They acted as filters, trapping certain wavelengths of light and allowing only the deep, vibrant red to pass through. Conversely, to achieve a brilliant green from the very same copper, the glassmaker would do the opposite. He would allow more air into the furnace, creating an oxidizing atmosphere. Now the copper would bind with oxygen, forming a different chemical compound that selectively filtered light to produce an emerald hue. This was a staggering level of control, achieved through centuries of trial and error, all without a single textbook or the concept of a molecule. The craftsman knew that a slight adjustment to the fire's air supply could mean the difference between a sacred crimson and a mundane green. He was conducting complex chemistry, manipulating matter at a nanoscale, guided only by the empirical evidence of his own eyes. The mystery of why these colors appeared was locked within the behavior of light itself, a secret the glass was about to reveal. These immense windows were not a stylistic choice, they were a structural necessity. The Gothic cathedral, with its soaring vaults and vast walls, presented a fundamental problem. How do you fill these enormous stone skeletons with something that keeps out the rain and wind, yet invites in the divine essence of light? Solid stone would have created dark, cavernous spaces. Stained glass became the ingenious solution, a material that was both a wall and a window. It transformed the architecture from a heavy fortress into a luminous vessel. But the clergy had a very specific vision for this light. It was not meant to be mere illumination. It was intended as a form of visual theology. The bishop would commission a window depicting the life of a saint and demand a particular celestial blue for the heavens or a deep, sacrificial red for a martyr's blood. These were not arbitrary color choices. They were symbolic instructions, a code that every worshipper, literate or not, could understand. The glassmaker, therefore, was not just an artist. He was a contractor fulfilling a precise order. His workshop's reputation and livelihood depended on his ability to deliver that exact shade of blue, batch after batch, for a window that might contain thousands of individual pieces. This relentless commercial pressure, the need for consistency and brilliance, is what fueled 5 centuries of quiet experimentation. They were not trying to prove a scientific theory. They were trying to please a demanding client and create a product that would last for generations. In doing so, they perfected a process of filtering light that was, in effect, a sophisticated technological practice. Their success in consistently producing those vibrant reds and blues is proof that they had mastered a repeatable chemical process, a controlled manipulation of light's behavior long before that behavior had a name. This transformation in the crucible was the glassmaker's daily reality. He would plunge his long, iron-stirring rod into the seething pot and watch as a pinch of metallic powder worked its alchemy. Cobalt oxide did not just dye the glass, it awakened a specific blue from within the chaos of light. In that molten state, he was witnessing a fundamental truth. The cobalt ions acted as a gatekeeper, absorbing the warm hues of red, orange, and yellow, but freely permitting the cool, blue wavelengths to travel through. The glass itself was not blue, it was a filter that created blueness by subtraction. The same principle held for that legendary ruby red, achieved by suspending vanishingly small particles of gold within the clear matrix. These nanoparticles did not absorb light in the same way, instead they scattered it, a phenomenon we now call the ruby glass effect. To the artisan, it was a simple, repeatable formula. Add this mineral under these fire conditions, and you get that exact color. They had built a vast, unwritten catalog of cause and effect. This was a working model of selective light absorption, a practical technology developed 500 years before Isaac Newton would use a prism to formally split white light into its constituent spectrum. The glassmakers did not know the theory of wavelengths, but their hands and eyes understood the result. Their craft was a form of embodied science, a knowledge stored not in books but in the consistent, brilliant colors of the windows they created. This deep, practical understanding allowed them to manipulate light with a precision that would baffle natural philosophers for centuries to come. Chartres Cathedral stands as the ultimate testament to this craft. Its windows are not merely decorations, they are a vast archive of optical knowledge, 1,000 experiments frozen in time. The most famous of these is the legendary Chartres blue. This is not just any blue, it is a specific, luminous shade, a celestial azure that seems to draw its brilliance from the sky itself. Achieving this exact hue consistently, across hundreds of individual glass panels created over decades, was a monumental feat. It required a master glassmaker who possessed a secret, repeatable recipe, most likely involving a precise blend of cobalt oxide melted under tightly controlled conditions. Each successful panel of that radiant blue was a verified result, proof that the formula worked. But for every perfect sheet of glass that was cut and set into the lead frames, how many failures were there? A batch that turned out a murky gray or a pale, washed-out imitation of the desired color was not just an artistic disappointment, it was a costly waste of materials and time, a clear sign that the alchemy had failed. This relentless cycle of trial and error, driven by the demands of sacred architecture, functioned as a massive, unplanned laboratory. The cathedral itself became the testing ground. Each window was the final report on thousands of hours of experimentation, a published result demonstrating a profound, if unspoken, understanding of how to manipulate light through chemistry. The consistency of Chartres blue across the centuries is undeniable evidence that these artisans had perfected a scientific process, achieving a level of control that would not be formally understood for generations. Yet this luminous chemistry was only half the masterpiece. The true magic emerged when these brilliantly colored sheets were cut and assembled. Each piece of glass was cradled within a channel of lead, an H-shaped strip known as a came. The craftsmen soldered these cames together, creating a strong, flexible armature that could withstand wind and weather for centuries. But this lead network was far more than a structural necessity. It created a powerful visual effect, a stark black grid laid over the radiant sea of color. This contrast was not an accident, it was a deliberate artistic tool. The deep, dark lines of the lead forced the viewer's eye to focus intensely on the pure, vibrant color of the glass itself. By framing each fragment of light, the lead cames heightened the perceived luminosity, making the reds feel hotter and the blues feel deeper, as if the light was concentrated within each individual cell. Think of it as an ancient form of pixelation. The lead lines broke the grand image into thousands of tiny, discrete points of colored light. This framing did something remarkable. It made the unique behavior of light through each type of glass impossible to ignore. When you look at a window depicting a saint in red robes against a blue sky, the lead cames create a clear boundary. Your eye can easily compare the rich, warm glow of the red glass with the cool, celestial shimmer of the blue right beside it. This side-by-side comparison, enforced by the black grid, accentuated the fundamental difference in how each color interacted with light. It highlighted the fact that the red glass was filtering the light in one specific way, while the blue glass was filtering it in another. The lead, in its silent, structural role, was subtly teaching a lesson in optics. It framed the experiment, making the properties of light and color distinct and observable to anyone who gazed upward, turning the entire window into a comparative display of light's hidden nature. This meticulous craft, perfected in fire and shadow, was not entirely lost to whispers and workshop secrets. We are granted a remarkable window into this world through the words of one man, a German monk known as Theophilus Presbyter. Around the year 1125, Theophilus compiled a vast work titled On Various Arts, a comprehensive manual detailing the practices of painters, metalworkers, and glassmakers. This was not a book of abstract philosophy or theological debate. It was a practical, step-by-step guide, a compilation of recipes that had been proven to work. Theophilus provides explicit instructions, for example, on how to create a sapphire-colored glass. He directs the artisan to mix the molten sand with a specific mineral he calls sapphire stone, which we now know was almost certainly a cobalt ore. His writing confirms that the creation of these brilliant colors was not a matter of chance or magical incantation. It was a standardized, repeatable process, a technology that could be taught from one master to an apprentice. Theophilus was recording a body of working knowledge that implicitly understood how matter and light interacted. He knew that adding this particular stone to the fire would consistently yield that specific heavenly blue. This written record transforms the stained glass window from a beautiful object into a documented scientific achievement. It proves that the glassmakers possessed a deep, systematic understanding of their materials, an understanding so reliable it could be written down as a formula for others to follow, centuries before the science behind it would be formally explained. The quest for perfect color was only one side of the glassmaker's challenge. For every expanse of celestial blue or ruby red, there were crucial details that demanded a different kind of light. The serene face of a saint, the delicate hands of an angel, these human elements required a far more transparent medium, a clear or lightly tinted glass that would allow the painted features to shine through. Yet achieving perfect optical clarity was an impossibility in the medieval workshop. The glass they produced was a living record of its creation, often rippled with the texture of its molten state, dotted with tiny air bubbles trapped during the furious stirring, and varying slightly in thickness from one edge to the other. These were not flaws to be hidden, but simply the inherent character of the material, and it was within these very imperfections that another secret of light lay hidden. When a craftsman held a newly cooled sheet of this clear glass up to the window, he witnessed a private show of optics. The sunlight, passing through a tiny bubble, would bend around its curved surface, creating a distorted, shimmering view of the world outside. Along the edge of a thick ripple, he might see a faint but unmistakable fringe of color, a ghost of a rainbow. This was the phenomenon of refraction, the bending of light as it passes from one medium, like air, into another, like glass, and then back out again. The thicker the glass or the more pronounced the curve, the more pronounced the bend. They saw dispersion too, the splitting of white light into its constituent colors, happening right there on the surface of their own handiwork. A master glazier, cutting these panes for a face or a hand, learned to read these imperfections. He would intuitively select a piece where the ripples and bubbles would not grotesquely distort the painted features, perhaps even positioning a bubble to catch the light in a way that added a divine sparkle to an eye. They had no concept of Snell's law, the mathematical formula that predicts the angle of bending, but their hands and eyes developed a profound practical grasp of its effects. Their daily labor was a continuous, unconscious experiment in geometric optics, teaching them how light behaves when it meets a curved, transparent obstacle. The cathedral window, therefore, became more than a color filter. It was also a complex lens, a vast array of imperfect prisms that subtly fractured and redirected the sunlight pouring into the nave, adding a dynamic, living quality to the sacred stories told in glass and lead. The cathedral itself became the ultimate collaborator in this grand optical experiment. Gothic architects were not merely constructing a building, they were engineering a vessel for divine illumination. Their revolutionary designs transformed solid stone skeletons into vast, intricate cages of light. The soaring height of the nave was punctuated by rows of clerestory windows, high above the ground, designed to capture the pure, untarnished light from the sky. Outside, the elegant arches of flying buttresses worked like stone spiderwebs, supporting the immense weight of the vaults and allowing the walls between them to dissolve into vast expanses of glass. This was a radical departure from the dark, fortress-like churches of the past. Every aspect of the structure was calculated to invite light in, to channel it, and to make it dance within the sacred space. The very orientation of the cathedral was a deliberate choice, aligning the main windows to catch the sun's journey from dawn to dusk. This architectural genius meant the stained glass was never viewed under a single, static light. It was a dynamic, living canvas, from the first gentle rays of morning that set the windows ablaze with a soft, internal fire, to the high, piercing light of noon that saturated every color with almost unbearable brilliance. The glass was in constant dialogue with the sun. The master glassmaker, visiting his finished work, would witness the full performance of his craft. He saw how a particular shade of blue, mixed in his crucible months before, took on a deep, mysterious quality in the oblique light of sunset. He observed how the intensity of a red could shift from a warm glow to a fiery beacon as the sun climbed higher. This daily cycle provided an involuntary but incredibly valuable masterclass in optics. It demonstrated clearly that the color was not a fixed property of the glass alone, but a product of the interaction between the glass and the ever-changing light. The cathedral amplified their discovery, turning each window into a lecture on how the angle and intensity of incident light fundamentally alter our perception of color. This distinction between practical recipe and abstract theory lies at the heart of their silent achievement. The medieval glassmaker possessed a deep, reliable knowledge of what would happen, but he had no understanding of why it happened. His expertise was a language of action and reaction, a vocabulary built around substances and furnace conditions. He knew with absolute certainty that adding a specific cobalt ore to the molten sand under a specific fire would yield a brilliant blue. This knowledge was as dependable as knowing that planting a seed in spring would yield a harvest in autumn. It was a functional truth verified by countless repetitions in the workshop. What he did not have was the concept of white light being composed of a rainbow of different wavelengths. The idea that his blue glass worked by absorbing the longer red and yellow wavelengths, allowing only the shorter blue waves to pass through, would have been an alien abstraction. His world was one of tangible cause and tangible effect, not invisible spectra. This empirical knowledge, this recipe-based science, is a form of power. It allows you to change the world, to create stunning beauty without requiring a lecture on the underlying physics. It is the knowledge of a master chef who can create a perfect soufflé every time, guided by touch and sight, without ever needing to diagram the complex chemical reactions taking place in the oven. The glassmakers were masters of the how, not the why. And in many ways, this makes their centuries of success even more astounding. They built a towering edifice of optical technology using only the bricks of observation, trial, and error. They were navigating a complex natural phenomenon with a map that showed only the landmarks, not the physical laws of the terrain itself. Theirs was a science of the hands and the eyes, a profound intelligence expressed not in equations but in the consistent, radiant proof of their craft. Yet this story of discovery was never confined to the cold northern workshops of Europe. The same light that streamed through the windows of Chartres was also being studied with intense curiosity under the brilliant sun of the Middle East. While European glassmakers were mastering the how, Islamic scholars were pioneering the why. In the 11th century, the Persian scientist Ibn al-Haytham, known in the West as Al-Hazan, was composing his monumental book of optics. This was not a book of recipes, but a revolutionary work of theory. Al-Hazan correctly argued that vision occurs when light rays travel from an object into the eye, overturning the ancient Greek idea that the eye itself emitted light. He conducted meticulous experiments with lenses, mirrors, and camera obscuras, laying the formal groundwork for the science of optics. His work described reflection and refraction with a mathematical precision that was entirely absent from the European craft tradition. This intellectual revolution was happening concurrently with the construction of the great Gothic cathedrals, a parallel stream of inquiry into the nature of light. The pathways for this knowledge to travel were already well worn. Through the bustling trade routes that connected the Mediterranean world, through the complex cultural exchanges in the vibrant courts of Sicily and Spain, and even through the violent contact of the Crusades, ideas had a way of seeping across borders. It is unlikely that a master glassmaker in France would have read Alhazen's dense Arabic texts, but the educated monks who designed the cathedral's iconography, or the wealthy bishops who commissioned the windows, may well have been exposed to these new ideas. A patron might not understand the mathematics of refraction, but he could grasp the revolutionary concept that light behaves according to consistent, observable laws. This intellectual environment, subtly fertilized by imported knowledge, could have encouraged a greater appreciation for the manipulation of light itself, creating a climate where the artisan's brilliant colors were seen not just as decoration, but as a manifestation of a divine and orderly cosmos. The glassmakers provided the stunning practical proof, while a whisper of theoretical understanding carried along ancient trade routes may have helped the world see their work for the scientific miracle it truly was. Far from the roaring furnaces of the glasshouse, in the quiet scriptorium of a monastery, another artist was conducting a similar set of experiments with light. Here, the medium was not molten sand but parchment, and the light source was not the sun but the flickering flame of a candle. The manuscript Illuminator faced a parallel challenge: how to make biblical scenes radiate with a divine luminosity on a flat, dry surface. Their palette was surprisingly familiar, built from the very same metallic and mineral sources. To create a blue that rivaled the sky, they would grind lapis lazuli, a semi-precious stone imported from distant Afghanistan, into an exquisite and costly powder. A rich red might come from vermilion, a pigment derived from mercury sulfide. Their workshop was an alchemist's bench of crushed minerals and binding agents. But the Illuminators' true genius lay in the application. They understood that color was not merely a layer of paint, but a tool to manipulate light itself. By applying pigments in thin, translucent glazes, they could build up depth and intensity, allowing the white of the parchment underneath to reflect light back through the color, giving it a glowing internal quality. This technique created a visual effect strikingly similar to light passing through a pane of stained glass. The most dramatic manipulation, however, was reserved for gold. The application of gold leaf was a meticulous process. A section of the parchment would be treated with a sticky adhesive called gesso, raised slightly from the page. Then the artisan would carefully lay down a wafer-thin sheet of genuine gold. Once burnished with a smooth stone, the gold would not just sit on the page, it would become a mirror. Under the shifting light of a candle, the gold leaf would seem to come alive, shimmering and flashing as the viewer moved. It captured the ambient light in the room and gave it back as a brilliant, metallic glow, making halos and heavenly backgrounds appear to emit their own sacred radiance. The illuminator, like the glassmaker, was not just applying color, they were engineering an interaction between material and light. One worked with transmitted light, filtering the sun's rays through colored glass. The other worked with reflected light, bouncing candlelight off colored pigments and metallic leaf. They were two different answers to the same fundamental question: how can a human hand command light to create a sense of the divine? This parallel pursuit, unfolding simultaneously in glass and on parchment, points to a broader, intuitive movement. It suggests that the drive to understand and control light's behavior was not an isolated accident in a single craft, but a widespread intellectual current flowing through the artistic soul of the Middle Ages. This brilliant, practical understanding of light was never destined for the halls of academia. The glassmaker's workshop was a world apart from the university library, separated by a deep social divide that knowledge struggled to cross. These artisans were masters of a manual trade, respected for their skill but not considered philosophers. Their insights were not written as formal propositions to be debated by scholars. They were guarded trade secrets, the lifeblood of a family business or a guild's monopoly. A master would whisper his most prized recipes only to a trusted apprentice, often his own son, ensuring the competitive advantage survived for another generation. This knowledge was a form of capital protected as fiercely as a chest of gold. To write it down for public consumption would have been unthinkable, an act of economic self-sabotage. Meanwhile, in the universities, learned men known as scholastics were engaged in a different kind of pursuit. They debated the nature of light and color through the lens of ancient authorities like Aristotle, using logic and scripture to construct complex philosophical arguments. Their world was one of texts and disputations, far removed from the soot and fire of the workshop. A scholastic philosopher would have seen a stained glass window as an illustration of divine glory, not as a dataset proving a principle of optics. The very idea that profound truths about the natural world could be discovered by a common craftsman through manual labor would have been dismissed. The two worlds operated on entirely different frequencies. The craftsman communicated in the language of hands and materials, the scholar in the language of words and ideas. There was no shared journal, no scientific society, no mechanism to translate the glassmaker's proven recipe for ruby red into a theoretical challenge to Aristotelian physics. The knowledge was trapped, a brilliant signal broadcast from the workshop that the academic world was not equipped to receive. It remained a silent, embodied science, glowing in cathedral windows for all to see, yet its deepest meaning remained locked away for centuries, waiting for a mind that could bridge the gap between practical craft and theoretical inquiry. The geometric lines of the lead cames had framed color for all to see, but a new kind of line was about to change how the world understood vision itself. In the sun-drenched piazzas of Renaissance Italy, artists were beginning to dissect the very act of seeing. They grew dissatisfied with the flat, symbolic representations of the medieval world, yearning instead to capture the world as the eye truly perceived it. This was not just an artistic impulse, it was a philosophical one, and it required a radical new theory of light. The breakthrough came from the architect Filippo Brunelleschi, who demonstrated linear perspective around 1420. He painted the Florence baptistery on a small panel, then drilled a tiny hole through it. When a viewer looked through the hole from the back, with a mirror held in front of the painting, the reflection of the artwork aligned perfectly with the actual building behind it. This famous experiment proved a profound truth. Vision could be understood as a pyramid of straight lines, with the eye at the apex and the scene spreading out at the base. Light, it seemed, traveled in straight, measurable rays from every point on an object directly to the observer. Leon Battista Alberti later codified this idea in his treatise on painting, providing artists with a practical method, the vanishing point, to recreate this optical pyramid on a flat surface. This was a monumental shift. For the first time, light was being treated not as a mystical emanation, but as a geometric phenomenon that could be mapped with a ruler and compass. The medieval glassmaker knew how to filter light to create color. The Renaissance artist was now learning how to trace its path to create space. They were developing a visual language of rays and angles, a conceptual scaffold that would eventually be necessary for someone like Newton to even conceive of light as something that could be split, measured, and analyzed. The canvas was becoming a diagram of optics, a silent preparation for the scientific revolutions to come. The straight lines of perspective were a prelude to a more profound dissection of light. Isaac Newton's famous Prism experiments in the 1660s did not occur in a vacuum. For centuries, artisans had watched rainbows dance in the imperfections of their glass. Newton's singular achievement was to take this common observation and subject it to ruthless, systematic inquiry. His genius was not in seeing the spectrum, but in demanding an explanation for it. He darkened his room, allowing only a single beam of sunlight to enter through a slit. He directed this pure, narrow ray through a triangular prism and watched it explode into the familiar band of colors on the far wall. But he did not stop there. This was the crucial difference. He then used a second prism to try to recombine the colors back into white light. He measured the angles of bending for each distinct hue. He was not content with the beautiful effect, he was obsessed with its mechanism. From this meticulous work, he proposed a revolutionary idea. White light is not a pure, simple entity. It is a mixture, a composite of all the colors of the spectrum. The prism did not create color, it merely separated what was already there. Furthermore, he concluded that each color had its own immutable identity within the beam, a specific property we now call a wavelength, and that refraction was wavelength dependent. A prism bends blue light more sharply than red light because their wavelengths are different. In that moment, the scattered, practical knowledge of the glassmakers was suddenly framed by a universal law. Newton transformed the medieval craftsman's reliable recipe into a fundamental principle of physics. He answered the why that had eluded the artisans for generations. He moved the understanding of light from the workshop, where the focus was on how to produce an effect, into the academy, where the goal was to explain the cause. The colored glass of the cathedral was no longer just a sacred filter. It was a demonstration of a cosmic truth, its secret finally spoken aloud. Newton's own notebooks reveal a mind obsessed with the hidden properties of matter, an alchemist's quest that ran parallel to his more public work in physics. He spent countless hours in his private laboratory, heating metals, mixing compounds, and documenting the strange colors that emerged from his furnaces. In these secretive experiments, he was engaged in a practice that would have felt deeply familiar to a medieval glassmaker. He was observing how specific materials, when subjected to heat, could transform and produce stunning visual effects. The same metallic oxides that created the ruby red of a cathedral window, gold and copper, were also the subjects of Newton's meticulous alchemical investigations. While he never explicitly wrote about visiting Chartres or studying its blue glass, the raw materials of his inquiry were identical. The empirical knowledge of color production was not locked away entirely in the guild halls. It had seeped into the vast body of alchemical literature that Newton devoured, texts filled with recipes for creating luminous substances and transforming base materials. These books were often cryptic, a mix of practical instruction and mystical symbolism, but they preserved centuries of workshop experience. A recipe for a particular red glass, passed down through generations of artisans, might appear in an alchemical manuscript as a formula for achieving a philosophical transformation. Newton, with his voracious and eclectic reading, would have encountered these descriptions of color changes and material interactions. He may not have credited a forgotten glassmaker, but the patterns were there, a scattered record of cause and effect, waiting for a mind capable of seeing the underlying law. The path from the artisan's furnace to the scientist's prism was not a straight line, but a slow, meandering river of accumulated observation. The glassmakers provided the countless data points, the repeated, proven results that color could be reliably manufactured from matter. Newton's genius was to look at that entire body of practical evidence, both written and unwritten, and ask the single, revolutionary question that the craftsmen never needed to voice. Why must it always work this way? He took their flawless recipe and uncovered the fundamental physics that made it inevitable. The silent science of the windows finally found its voice in his theory of the spectrum, completing a collaboration across centuries that neither party could have ever anticipated. This deep understanding of glass as a material did not simply fade when the last great cathedral was completed. The very same mastery over molten silica, the same hard-won control of clarity and curvature, found a startling new purpose in a small Italian workshop around the end of the 13th century. The invention was eyeglasses, and it was born directly from the glassmaker's art. Creating a window pane was one thing, but shaping a small, perfectly curved lens was an even greater challenge. It demanded a level of control that only centuries of furnace work could provide. The artisan had to produce a bubble of glass that was remarkably free of the ripples and bubbles that characterized cathedral glass, then grind and polish it into a precise convex shape. This was not a random discovery, it was a logical evolution. The same craftsmen who intuitively understood how a curved glass surface could bend light to create a faint rainbow in a flawed pane, now applied that knowledge to bend light deliberately, focusing it onto the failing retina of an aging scholar. The leap from a sacred window to a vision-correcting lens was surprisingly short. Both were tools for managing light, one to inspire the soul, the other to assist the eye. The glassmaker's workshop, once dedicated to filtering divine light for the masses, now produced a personal device that extended the power of human sight itself. This was perhaps the most democratic legacy of their craft, transforming an understanding of optics from a monumental spectacle into a handheld miracle. Centuries of intuitive craftsmanship are now meeting the cold, precise gaze of modern science. We no longer have to guess at the secrets locked within the glass, we can simply ask the light itself. Researchers now use a technique called spectroscopy, shining a controlled beam of light onto a priceless medieval panel. By analyzing how that light is absorbed or reflected, they can read the glass' unique chemical signature, a fingerprint left by the original artisan. Another tool, X-ray fluorescence, can pinpoint the exact metallic elements present, revealing whether a deep blue came from cobalt or a more exotic mineral. This is not guesswork, it is definitive proof. The analysis reveals an astonishing level of consistency, batch after batch, proving that the medieval workshop was a place of rigorous quality control, not mystical chance. But the most stunning validation comes from the legendary ruby red glass. For generations, artisans knew that a tiny amount of gold, melted under the right conditions, produced that unparalleled crimson. Modern electron microscopes have shown us why. The red color is created by nanoparticles of gold, particles so small they are measured in billionths of a meter, suspended evenly throughout the glass. These nanoparticles scatter light in a specific way, a phenomenon known today as the colloidal gold effect. This scientific principle was not formally described until the 1800s by Michael Faraday. Yet medieval glassmakers with no concept of nanotechnology were producing and controlling this effect with flawless precision 500 years earlier. Their empirical recipe was, in fact, a highly advanced nanotechnological process. Science is now providing the explanation that was always missing, confirming that these artists were not just creators of beauty, but masters of material science who achieved a level of control over matter that we can only fully appreciate with the tools of the 21st century. The true darkness of the so-called Dark Ages was not a lack of intelligence, but a failure of historical perspective. This narrative of a backward, superstitious millennium collapses under the weight of the evidence glowing in every cathedral window. The medieval mind was not lost in shadow. It was brilliantly focused on solving tangible, monumental problems. Its genius was not expressed in theoretical treatises, but in the soaring stone of Gothic architecture and the radiant chemistry of stained glass. This was an age of profound applied science, where the drive to build and create beauty pushed technology to its absolute limits. The glassmakers' mastery over light was not an isolated miracle, but a testament to a culture capable of sustained, complex innovation. This forces a radical rethinking of scientific progress itself. We often imagine it as a straight, upward line, a sequence of brilliant minds like Newton building directly upon one another's theories. But the story of medieval glass reveals a far more complex and interesting reality. Progress can be a hidden river flowing underground for centuries, nourished by the practical needs of artisans and craftsmen. The desire to glorify God with a specific, celestial blue was a powerful enough motivator to fuel 500 years of meticulous experimentation. This practical need drove a deeper understanding of material science than any abstract curiosity could have achieved at the time. The resulting knowledge, the reliable recipe for color, was a form of science in action, even if it lacked the formal language of physics. The implications are profound. It suggests that some of humanity's greatest discoveries are not born in the quiet of a study, but in the roaring heat of a workshop. They are forged by the hands of those solving immediate, real-world challenges. The glassmakers did not set out to understand the nature of light. They set out to fulfill a sacred commission. Yet, in doing so, they unlocked a fundamental truth about our universe. Their knowledge then lay dormant, a secret held within the very fabric of their creations, waiting for a future generation with a different set of questions. This is not a story of failure, but of a different kind of success. It reminds us that the capacity for discovery is universal, and that the path to understanding is often paved with practical necessity, a legacy of innovation that shines down on us still. This separation of art and science was not an inevitable fate, but a historical choice. The medieval master craftsman, like our glassmaker, saw no such division. His hands shaped the material while his mind analyzed its behavior, a continuous loop of thought and action. He was an artist-scientist in a single skin, his workshop a laboratory where beauty and truth were forged together. But the currents of history began to pull these two ways of knowing apart. The scientific revolution, for all its brilliance, championed a new kind of knowledge, one based on mathematics, abstraction, and the authority of the written text. The world was to be understood not by shaping it, but by measuring it. The artist, meanwhile, was increasingly celebrated for a different virtue, individual genius and emotional expression. The value of a work shifted from its technical mastery and symbolic function to the unique vision of its creator. A stained glass window, the product of a guild following a sacred formula, did not fit neatly into this new romantic ideal of the solitary artist. The painter in his studio and the physicist in his study were now seen as inhabiting different realms, one of subjective feeling, the other of objective fact. The deep, practical intelligence of the craftsman, the very intelligence that had built the cathedrals, was caught in the middle, no longer considered true science nor high art. It was dismissed as mere technique, a set of skills without a theoretical soul. This created a schism that would define our world for centuries, a divide between intuition and calculation, between making and modeling. We lost the holistic understanding that the glassmaker embodied, the synergy between hand and mind that turns raw material into a vessel of light. Yet today, in the most advanced workshops of our time, we see a fascinating return to this unified spirit. In biodesign, artists and engineers collaborate to grow living materials. In digital fabrication, a designer's concept flows seamlessly into a machine's precise execution. We are slowly, tentatively, rediscovering the power of the medieval model, where the act of creation is itself the deepest form of inquiry. The silent lesson of the stained glass window is not just about light, but about a way of being in the world, one where the artist and the scientist are once again the same person. You can recreate the core of their discovery right now with a simple flashlight and a piece of colored plastic. Shine the white beam through a red transparency, and the wall glows crimson. The plastic is not adding red to the light, it is subtracting everything else. It acts as a gatekeeper, absorbing the green and blue wavelengths and permitting only the red to pass. This is the essence of selective transmission, the very principle the glassmakers mastered. Now try layering that red sheet with a blue one. The result is not a brighter light, but a deep, murky purple or even near darkness. The two filters together block almost the entire spectrum of white light. This simple experiment reveals a profound truth about color. It is not an inherent property of an object, but an action, a process of filtration. The medieval artisan performed this same experiment every day, but on an infinitely more complex scale. His colored plastic was a crucible of molten sand and metal oxides. His flashlight was the sun itself. He knew that a specific blend of cobalt would create a blue filter so pure it seemed to capture a piece of the sky. He understood that layering a piece of this blue glass over a piece of yellow would produce a specific shade of green, a result he could predict and repeat with stunning accuracy. His workshop was a laboratory of layered filters, where the final color of a window was the product of a deliberate, calculated subtraction of light. He built this understanding not from theory, but from thousands of hands-on trials, observing exactly what happened when light met his meticulously crafted materials. That dark purple you see when you layer the red and blue sheets, that was not a failure to him. It was a data point, a confirmed result in a vast, unwritten catalogue of optical interactions. The silence of the historical record speaks volumes about who was allowed to be remembered. While we celebrate the collective genius of the anonymous artisan, we must also listen for the whispers between the lines. Glassmaking was not solely a male domain. It was, for the most part, a family enterprise, a household business where every member contributed to the survival of the craft. In this bustling workshop, women were almost certainly present, their hands as vital as any. Their roles were multifaceted and essential. They would have been responsible for the meticulous preparation of materials, grinding minerals into the fine powders that created the brilliant colors. They likely managed the delicate process of painting the facial features and intricate details onto the cooled glass using special enamel paints. Beyond the furnace, they might have handled the accounts, negotiated with suppliers, and ensured the workshop itself functioned smoothly day to day. Is it so difficult to believe that a woman, spending her life surrounded by the alchemy of the furnace, would not also make her own observations? While stirring a pot of molten glass, she might have noticed how a slight variation in the heat altered the hue of a blue, or how a different grinding technique for a mineral produced a more vibrant red. Her insights, shared casually over a meal or as instruction to a child, would have subtly refined the family's secret recipes, generation after generation. These contributions are forever woven into the fabric of the craft, inseparable from the whole. To imagine these workshops as filled only with men is to ignore the social and economic reality of medieval life. Acknowledging the likely role of women does not rewrite history with new names, but it does paint a more truthful and complete picture. It recognizes that this practical science was a truly collective endeavor, built on the unrecorded intelligence of an entire household, a silent collaboration that helped shape the light of the great cathedrals. Even with our most advanced instruments probing the glass, fundamental questions about their process remain stubbornly unanswered. How did they achieve such breathtaking consistency across hundreds of panels without a single thermometer? Their only gauge was the color of the fire itself, a skill learned through a lifetime of watching the flames. They judged temperature by the faint glow of a heated iron rod or by the way the molten glass shimmered and flowed. This was an art of perception, a deep bodily knowledge passed from master to apprentice through demonstration, not description. The discovery of gold's unique power to create ruby red is an even deeper mystery. It seems almost accidental. A craftsman might have added a flake of gold to a batch, expecting perhaps a golden hue, only to pull from the crucible a glass of such deep, luminous crimson it must have seemed like a miracle. Perhaps a piece of gold jewelry fell into a vat of molten glass by chance, yielding a color so extraordinary it launched a new line of inquiry. This points to a workshop culture that was inherently experimental, where failures were not simply discarded but studied. A batch that turned an unexpected violet or an opaque brown was not just waste, it was valuable information. It told the artisan what not to do, but it might also have revealed a new, desirable shade. These happy accidents, these unplanned detours in the recipe, were likely the source of some of their most celebrated colors. The surviving windows represent only the successes, the final, perfected formulas. They are the tip of the iceberg. Beneath them lies a vast, invisible history of trials and errors, of shattered pots and discarded panes, a silent record of experimentation that we can only infer. The true depth of their intuitive, hands-on science may be far greater than the beautiful fragments left behind can ever tell us. The story of the medieval glassmaker is a powerful reminder that the pursuit of beauty can lead to profound truths. For centuries, we have celebrated the singular genius of figures like Isaac Newton, who gave us the language to explain light. But this narrative overlooks a deeper, more collaborative form of discovery. The true breakthrough was not a sudden eureka, a moment in a Cambridge study, but the slow, collective genius of generations of artisans, whose drive to create something magnificent for their community accidentally mapped the laws of optics. Their legacy challenges our very definition of science. We often picture it as a formal, academic pursuit, a world of white lab coats and complex equations. Yet here, in the soot and fire of a medieval workshop, we find a different model. Science as a lived practice, a knowledge built not from abstract curiosity, but from the urgent, tangible need to solve a problem. The client demanded a specific blue, and the only way to deliver it was through 500 years of meticulous, hands-on experimentation. This was science in action, even if it was never written down as a theory. The next time you find yourself standing in a cathedral, look up at those radiant windows. You are not just seeing a religious story told in light and color. You are looking at a vast, uncredited scientific manuscript, its pages written in glass and lead. Each vibrant panel is a confirmed result, a successful experiment in wavelength filtering and material science. It is a landmark achievement that reconnects the often separated worlds of art and science, reminding us that the human impulse to create and the drive to understand are two sides of the same brilliant coin. If this story illuminated a new perspective for you, we would love to hear your thoughts in the comments below, and subscribe for more journeys into the hidden history.